All right, well, welcome back. So in this section, we're going to continue playing this game of trying to identify what Alice's private information happens to be under the assumption of only knowing what the H is. So we get to put on our nice little witch's hat and continue playing the role of Eve and trying to poke at the armor of this Intrue and crypto systems. We know what the underlying kind of question is. Now we want to begin seeing how hard is this question. Kind of the big monster that is this assumption that we know H and we want to find F and G. Last section, we began poking at this thing with the terrible kind of weak little sword of brute force and just trying to cycle through a bunch of things that look like an F, multiply them by the H, and hope to get lucky and see the actual G emerge. The idea is that we ran through all possible Fs, multiplied them by the given H, and hope to get something that looks like a G. That's a pretty flimsy little sword, and it's not going to be very effective. We know that we have to test like 3 to the n over n things, and that's awful if the n becomes really, really big. So what we're going to be doing in this section is we're basically going to go rummaging around in our toolbox and grab a new tool to begin poking at this armor. And our tool here is going to be this super duper awesome sword that I wrote Lattice on, which is a very poorly drawn sword, and that looks kind of like a spaceship. So whatever, sword, spaceship, whatever you want to call it, that's going to become our tool that we're now going to begin poking at this question about. So what I mean by that is we're going to see this initial question of trying to identify F and G. That's still my big goal, is I want to know what those things are going to be. I know what the H is. So what we're going to do is we're actually going to begin constructing a very specific lattice. And this lattice has the property that F and G are going to live in it. So we're going to have to view these things as nice little vectors. We're going to have this very specific lattice that's going to be constructed with just public information. But within that lattice is going to live this private information of F and G. Moreover, the F and G are actually going to be one of the shortest vectors in that lattice. So the big connection that's going to occur here is that if we can solve this shortest vector or closest vector question, we can actually gain some insight as to what F and G are going to be. So the big goal in all of this is we're going to make this connection here, kind of doing all the formal guts of showing that these two worlds collide. And then we get to play around with using some of our lattice reduction algorithms that we saw before that actually give us some information about what some short vectors may be. Then we can chat about, okay, how big does the n need to be to make that those systems crash and burn, so we actually get some security out of this. So it's kind of a nice segue section that we have our original little system, we know some lattices, now we want to connect those two pieces. So we're going to show how we actually use this big old lattice sword. To help us out, we're actually going to revisit this question of how to do multiplication with these crazy little polynomials, this so-called star operation. So if you remember before, we can have polynomials f and g, which are going to be assumed as these little lists of length n. We can multiply these things together and then begin doing that reduction of exponents modulo n. So that was this star operation that we built up before, saw some functions that we've been using over and over and over since then. We know that the way that this multiplication is constructed is we're going to take f, multiply it by h. That's going to give me a polynomial or a list of length n. And each of those coefficients or entries of that list are going to be comprised by multiplying the f's and the h's together in a clever little fashion. The way that they're multiplied together is we're going to combine those little indices that add up to the index h or the index k that we happen to be looking at. So if I want to play with, let's say, n being 7 and not erase it, and if I wanted to think about multiplying f and h together, and if I wanted to look at, let's say, the C2 constant, so the thing that would then be corresponding to the third slot of that list, or the term that goes with the x squared. So the way C2 is then going to be constructed is I'm going to multiply all of these fi's and hj's together so that those two indices add up to a 2. So we get 0, 2, 1, 1, 2, 0. And then we're going to get a few other ones that are then going to reduce down into a 2 modulo 7. So 3 and 6, that adds up to a 9. The 9 reduces down to a 2. The 4 and 5, that makes a 9. 9 reduces down to a 2. 5 and 4, again a 9. 6 and 3, again a 9. So we can construct this little C2 by adding up all of these little expressions and then storing that as our C2. So that's what this crazy little formula, again, is going to do. So that was the CK definition in this little star operation. And that's great and dandy. We had it. It was awesome. We knew exactly how it worked. We've used it over and over again. It's a really tidy way to actually see some of this reduction emerge. What we want to do now is begin to morph away from that just a little bit, because we really want to begin viewing these things as nice little vectors and trying to combine them a little bit. So to give us kind of a viewpoint, we're going to start off with this very concrete example of F and H. So here's F is 1337143, so Leet and Mr. Rogers' favorite number, followed by our classic 8675309. When we multiply those two things together and do this little star operation, we end up getting this little vector or this little polynomial in return. And at the end of this, I'll cycle back and I'll show off the Sage code to remind you of how this multiplication actually emerged. What we want to do next is we want to begin seeing other ways that we can get this little vector to reemerge. And that's going to be key when we convert this into a lattice. So the way that we're going to do this is we are going to begin constructing a very specific matrix that's going to record all of those crazy little rotations that we saw in the last section. We're going to store all of those rotations as a matrix H. So the first row on it is then going to be all of those H naught through Hn minus 1. And then the second row is where we're going to do one rotation. So everything shifts to the right by 1. And then the next row after that is we're going to do the same thing where we shift everything to the right by 1. And we keep this shifting going all the way on down. That matrix is going to be key for us as we move forward. When we actually convert this problem of trying to identify F's and G's into a lattice, this matrix is going to be a portion of the big matrix M that we want to work with. So in the example of 8675309 for our H, the little H matrix is just going to be that rotation of all of those things. So 8675309, then the 9 gets broken off and put into the front, and then it's everything else. Then the 0 and 9 followed by those, then the 309, then everything else, and we keep that process going. So it seems fine enough, like great, we have this H. That doesn't really tell me anything overly interesting. It was like, great, I have a thing. Does that actually help me at all? The key here is that this specific matrix H paired with the matrix for F is actually going to give us information about how we can do multiplication between F and H. So rather than having to do the star operation, we can actually take this F and multiply it by this H matrix to see the exact same vector emerge on the back end. So to show how that's going to work, we can see the following. So if I take this big old matrix H, and I'm going to have my vector of my F. If I wanted to identify the third cell, let's say, so this little number right here, what we do to do vector matrix multiplication is this crazy little twisting action. So we're going to take that F, and then it's going to be connected with this third column. And what happens is that we match things up. So that 1 and the 7 are both essentially the first thing in that list. So we're going to multiply those things together. Likewise, the next thing in that list is going to be a 3 and a 6. So we multiply those together. And we keep this process going. The 3 and the 8 get multiplied together, and we go on down until it kicks out our final sum. So officially what's happening is we're taking that vector F and we're dotting it with that column of H. So we multiply things that match up, and then we add up the resulting terms. Here we can see that we get exactly the 139, which is great and dandy. If we push this all the way through and do that for any column that we want to, what you can see is that on the back end here, you get exactly that list that we saw when we did the star. So the star list of F and H emerged as this thing. So I was using our built-in star operation. And now what we can see is that when we do that vector of F multiplied by that matrix of H, so all of those crazy little rotations, the result is exactly the same list that we would have achieved when we did the star. So we wouldn't actually need to identify the star as long as we lean on this vector matrix multiplication. And I specifically like built up the star because not everybody's got a really solid background in linear algebra. So I wanted to be like, hey, here's the star operation. We can do anything we want to. It makes sense because it's polynomials and it reduces down super nicely and everything emerges. What this tells me is that all of that technically could have been avoided if we would have just introduced those coefficients as what would have emerged from F multiplied by this crazy matrix H. So it's kind of we're viewing it a little bit later, though it probably should have been viewed first, but then the definitions don't really make sense. Because it's nice to view those coefficients as honest to goodness, like, hey, multiply F and H together, extract the coefficient. What we can see here is that all those little coefficients genuinely come from all of those just little star operations that we saw before. And if you want to do it with just kind of old school symbols, you can see that very nicely as well. So if I have my F, which is going to be viewed as F naught through Fn minus 1. And if I were to multiply it by the third column there, well, what you see is you're going to again match terms up. So that third column starts with an H2 because it's H naught, H1, H2. Then it's going to be followed by an H1 because everything was rotated by 1. And then the third one, everything was rotated by 2. So it's H2, H1, H naught, and then it keeps that process going. So when I multiply those two green things and then match things up, you can see that we get F naught H2. We get F1 H1. We get F2 H naught. And then if you go all the way down to the bottom, you're going to see that the last entry in this list is Fn minus 1, and it's going to be multiplied by H3, which is that term. The term before Fn minus 1 would then be Fn minus 2, and that would then be paired with H4. So what you can see is that we get this giant big old sum of terms that are multiplied together. And if you stare at them long enough, you can see that we get F naught H2. Those indices add up to a 2. F1 H1, those indices add up to a 2. F2 H naught, those indices add up to a 2. Even the crazy ones on the end add up to a 2 when we view them modulo n. So we have Fn minus 1 plus H4. The n minus 1 and the 4, that adds up to n plus 2. Reduce that mod n, it kicks out a 2. Likewise, Fn minus 1 and H3, n minus 1 plus 3 is again an n plus 2, which reduces down into a 2. So this little term, C2, that emerges from this matrix multiplication is exactly the same term that would have emerged in the star operation. So C2 in the star land, we go way back to star land, C2 is exactly constructed by multiplying all these little terms such that the indices would add up to 2 modulo n. So they are the exact same definition, which is the true brilliance of all of this, is that multiplication of polynomials is identical to this vector matrix multiplication. It's just a little bit easier to do here, is that if you have some notion of how to do matrix multiplication, then you automatically know how to do multiplication of these polynomials. So it's pretty cool and it's pretty tidy. If you want to see it for a C naught, you could do the exact same thing. So here you can see that all of those terms are going to have indice values that add up to a 0. If you do it for a general term, so I have the HK column, well, if you multiply those two things together, you're going to get everything connected so that those indices add up to a K. So F0 HK, F1 HK minus 1, F2 HK minus 2, all the way on down to Fn minus 1 and HK plus 1. So you get exactly the structure that you're hoping to see. So it's super duper tidy and everything is great to see it all come into play.